Okay, good morning, friends. Now we are about to presentate our discussion, which is regression analysis. But before that, please leave a like and please subscribe to this channel. So, a multiple regression equation is the regression analysis described and tested the relationship between a dependent variable and a single independent variable x. The relationship between an x was graphically portrayed by a line. When there are two independent variables, the regression equation is as below. As you can see here, this is the equation, which is y-intercept equals to a plus coefficient for x1 or predictive variables plus coefficient for predictive variables x2 and b3 or coefficient for predictive variables 3 and etc. Into the question, please give an example of multiple regression. For your information, you guys have 3 minutes to answer this question, starting from now. Time remaining 1 minute. Thirty seconds remaining. Okay, so an example in daily life, here we can say that age and height can be described as follows. Now we move on, which is many statistics and statistical methods are used to evaluate the relationship between a dependent variable and more than one independent variable. Our first step was to write the relationship in terms of a multiple regression equation. The next step follows on the concepts of presented by using the information in an ANOVA table to evaluate how well the equation fits in the table. The ANOVA table. The statistical analysis of a multiple regression equation is summarized in an ANOVA table. To review, the total variation of the dependent variable y is divided into two components. The first one, which is regression, or the variation of y explained by all the independent variables, and the second one, the error or residual, or unexplained variation of y. The column headed df refers to the degrees of freedom associated with each category. The total number of degrees of freedom is n1. Excuse me, I mean n1. As you can see from the table below here. Now, we move on to question number 2. Why do we use ANOVA table? You guys have 3 minutes to answer this question, starting now. Forty seconds remaining. Okay, time is up. So here's an example of the answer. The ANOVA table is used to compare differences of two means among more than two groups. Okay, so now we will use the ANOVA table information from the previous example to evaluate the regression equation to estimate January heading costs. As you can see here in this table below, we have all the costs here: temperature, install, and age of each participant. Multiple standard error of estimate. To explain the details of the standard error of estimate, the actual heading cost for the first observation, Y, is $250, for example. The outside temperature is 35 degrees. The depth of insulation is 3 inches. And the age of the furnace is 6 years, from the table before. Using the regression equation developed in the previous section, the estimated heading cost for this home is as follows. So Y intercepts equals to 427,000 subtracted by 4,583 x1, or predictive variables, subtracted by 14,831 predictive variables 2, and added by 6.101 predictive variables 3. Now that we have all the result, we can do as follows here below, as you can see here. Into question 3. How do we find or calculate multiple standard error? You guys have 3 minutes to answer this question, starting from now. 1 minute remain. Seconds. Okay, time is up. To help you guys understand, here is the answer. The standard error is calculated by dividing the standard deviation by the sample size's square root. This gives the precision of a sample mean by including the sample-to-sample variability of the same sample means. If we repeat this calculation for the other 19 observations and sum all 20 squared differences, the total will be the residual or error sum of squares from the ANOVA table. Using this information, we can calculate the multiple standard error of the estimate as follows. Here you can see the multiple standard error of estimate equation, which is sy times 1, 2, and 3, or the variables x1, x2, and x3 dot k equals to the square root of summation, y subtracted by y-intercept to the power of 2 divided n minus k plus 1 equals to the square root of SSR divided by n subtracted by k plus 1. Here you can see that y is the actual observation and n is the number of observations in the sample. K is the number of independent variables. SSR is the residual sum of squares from an ANOVA table. The characteristics of the coefficient of multiple determinations are, first of all, it is symbolized by a capital R squared. In other words, it is written as because it behaves like the square of a correlation coefficient. The second one, it can range from 0 to 1. A value near 0 indicates little association between the set of independent variables and the dependent variable. A value near high means a strong association. The third one, it cannot assume negative values. Any number that is squared or raised to the second power cannot be negative. And the fourth and last, it is easy to interpret because it is a value between 0 and I. It is easy to interpret, compare, and understand. Symbol R2 is a numerical index that reflects the degree to which variation in a response or outcome variable, example, the worker's incomes, is accounted for by its relationship with two or more predictor variables. Example, age, gender, years of education. Here you can see the coefficient of multiple determination equation, which is R2 equals to SSR divided by SS total.
Adjusted coefficient of determination. So the adjusted coefficient of determination or adjusted R square is an adjustment for the coefficient of determination that takes into account the number of variables in the data set. It also penalizes you for points that don't fit the bill. As you can see, here's the formula. So adjusted R square equals to 1 minus open brackets, open parenthesis 1 minus R square, close parenthesis times open parenthesis n minus 1 close parenthesis divided by n minus k minus 1 close brackets, where n is the number of points in your data sample and k is the number of independent regressors, the number of variables in your model excluding the constant. So this is the question number 4. Why do we use adjusted R square? What is this for? Once again, question number 4. Why do we use adjusted R square? What is this for? You have 3 minutes to answer this question. Starts now. One minute left to answer the question. Time is up, guys. So the answer for the question number 4 is to find out how the independent variable explain the dependent variable if the researcher uses more than 2 independent variables. Meaning of adjusted R-square. Both R-square and the adjusted R-square give you an idea of how many data points fall within the line of the regression equation. However, there is one main difference between R2 difference between R2, R square and the adjusted R square. R square assumes that every single variable explains the variation in the dependent variable. The adjusted R square tells you the percentage of variation explained by only the independent variables that actually affect the dependent variable. How adjusted R square penalizes you? The adjusted R square will penalize you for adding independent variables or K in the equation that do not fit the model. Why? Because in regression analysis, it can be tempting to add more variables to the data as you think of them. Some of those variables will be significant, but you cannot be sure that significance is just by a chance. The adjusted R square will compensate for this by that penalizing you for those extra variables. While values are usually positive, they can be negative as well. This could happen if your R square is 0. After the adjustment, the value can dip below 0. This usually indicates that your model is a poor fit for your data. Other problems with your model can also cause sub-zero values, such as not putting a constant term in your model. Okay, question number 5. What happens if the adjusted R square value is negative? Once again, question number 5. What happens if the adjusted R square value is negative? You have 3 minutes to answer this question, starting now. 1 minute left, guys, to answer the question. Time's up, guys. So here is the answer. The value of adjusted R-square can be negative. So if the value is negative, then the value is considered zero, or the independent variable is completely unable to explain the variance of the dependent variable. Problems with R-square that are corrected with an adjusted R-square. First, R-square increases with every predictor added to a model, as R-square always increases and never decreases. It can appear to be a better fit with the more terms you add to the model. This can be completely misleading. Second, similarly, if your model has too many terms and too many high-order polynomials, you can run into the problem of overfitting the data. When you overfit data, a misleadingly high R-square value can lead to misleading projections. Inferences in multiple linear regression. Multiple linear regression analysis is a linear relationship between two or more independent variables, with the dependent variable is y. This analysis is to determine the direction of the relationship between the independent variable and the dependent variable, whether each independent variable is positively or negatively related, and to predict the value of the dependent variable if the value of the independent variable increases or decreases. Here is the multiple linear regression equation. So y prime equals to a plus b1x1 plus b2x2, etc., where y prime equals to dependent variable or predicted value. x1, x2 equals to independent variables. A equals to constant, or the value of y prime if x1, x2, etc. equals to 0. And the last one is B. B is regression coefficient, or increase or decreases value. Global test, testing the multiple regression model. We can test the ability of the independent variables to explain the behavior of the dependent variable. The test used is referred to as the global test. Basically, it investigates whether it is possible all the independent variables have zero regression coefficients. So in testing a hypothesis, we first state the null hypothesis and the alternate hypothesis. The null hypothesis is H0 is beta 1 equals beta 2 equals beta 3 equals 0. While the alternate hypothesis is H1 is not all the betas is R0. The numerator is the regression sum of squares divided by its degrees of freedom. The denominator is the residual sum of squares divided by its degrees of freedom. The formula follows. So F equals to SSR per K divided by SSE per in brackets N minus open parenthesis K plus 1 plus parenthesis in brackets, where SSR equals to sum of squares regression, SSE equals to sum of squares error, and number of sample, and K number of independent variable. Evaluating individual regression coefficients. The independent variables individually to determine which regression coefficients may be 0 and which are not. Why is it important to know if any of the equal 0? If a could equal 0, it implies that this particular independent variable is of no value in explaining any variation in the dependent value. If there are coefficients for which H0 cannot be rejected, we may want to eliminate them for the regression equation. Testing individual regression coefficients. The formula T equals BI minus 0 divided by SBI. That refers to any one of the regression coefficients and refers to the standard deviation of that distribution of the regression coefficient. We include beta 0 in the equation because the null hypothesis is. So here we have the Minitab output where heating cost is the dependent variable and outside temperature and amount of insulation are the independent variable. So summarizing the results from this new Minitab output. Here we go. So the step 1, the new regression equation is y prime equals to 490.29 minus 5.1499x1 minus 14.718x2. Notice that the regression coefficients for outside temperature and amount of insulation are similar to, but not exactly the same as when we included the independent variable age of the furnace. Step 2. This is the null hypothesis and the alternate hypothesis. The F distribution is the test statistic and there are degrees of freedom in the numerator and degrees of freedom in the denominator. Using the 0.5 significance level and appendix B.4, the decision rule is to reject if F is greater than 3.59. We compute the value of F as follows. So F equals SSR per K divided by SSE per in brackets N minus in parentheses K plus 1 close brackets equals to 165.195 per 2 divided by 47.721 per in parentheses 20 minus in brackets 2 plus 1 plus brackets equals 29.42. Because the computed value of F, which is 29.42, is greater than the critical value, which is 3.59, the null hypothesis is rejected and the alternate is active. We conclude that at least one of the regression coefficient is different from 0. Using the p-value, the F-test statistics, which is 29.42, has a p-value, which is 0.000. that is clearly less than 0.05. Therefore, we reject the null hypothesis and accept the alternate. We conclude that at least one of the regression coefficient is different from 0. Step 3, the last one, to find out if one or both of the regression coefficients are different from 0. The null and alternate hypotheses for each of the independent variables are f equals SSR per k divided by SSE per in parentheses and minus in brackets k plus 1 close brackets equals to 165.195 per 2 divided by 47.7 to 1 divided in brackets 20 minus in brackets 2 plus 1 close brackets equals 29.42. The test statistic is the t distribution with n minus in brackets k plus 1 equals 20 minus in brackets 2 plus 1 equals 17 degrees of freedom. Using the 0.05 significance level and appendix B.2, the decision rule is to reject if the computed value of t is less than minus 2.110 or greater than 2.110. So the outside temperature T equals B1 minus 5.1499 minus 0 divided by 0.7091 equals minus 7.34. For insulation, T equals B2 minus 0 divided by SB2 equals minus 14.718 minus 0 divided by 4.934 equals minus 2.98. In both tests, we reject and accept. We conclude that each of the regression coefficient is different from 0. Both outside temperature and amount of insulation are useful variables in explaining the variation in heating costs. Evaluating the assumptions of multiple regression. The results of the test let us know if at least one of the coefficients was not equal to 0, and we describe a procedure of evaluating each regression coefficient. We also discuss the decision-making process for including and excluding independent variables in the multiple regression equation. Now, linear relationship. So linear relationship is a statistical measurement between two variables in which changes that occur in one variable cause changes to occur in the second variable. Measuring linear relationship on a graph results in a straight line, where the line the variables create increases, decreases, or remains constant, such as horizontal or vertical lines. So this is question number 6. Please give examples of linear relationship in daily life. Once again, question number 6. Please give example of linear relationship in daily life. You guys have 3 minutes to answer this question, starting from now. Okay, time is up. So the answer is, here's some of example of linear relationships are very common in everyday life. Example, Nikki and Jay's hikes and Alice runs.
Linear relationship. Now, using residual plots, recall that a residual can be computed using the multiple regression equation for each observation in a set data. And variations in residuals, same for large and small values. Now, this requirement indicates that the variation about the predicted values is constant, regardless of whether the prediction values are large or small. To cite a specific example, which may violate the assumption, suppose we use the single independent variable h to explain the variation in income. We suspect that as age increases, so does salary. But it also seems reasonable that as age increases, there may be more variation around the regression line. Now, there is also homoscedasticity, which is the variation around the regression equation, is the same for all of the values of the independent variables. And there is distribution of residuals. Now, in order to make the valid inference from your regressions, the residuals of the regressions should follow a normal distribution. The residuals are simply the error terms or the differences between the observed value of the dependent variable and the predicted value. Now, if we examine a normal predicted probability, which is PP for plot, we can determine if the residuals are normally distributed. Now, if they are normally distributed, they will conform to the diagonal normality line indicated that in the plot. We will show what this looks like a little bit later. And this is the distribution of residuals. In this case, both the graphs in the picture support the assumption that the residual follows the normal probability distribution. Therefore, the inferences that we made based on the global and individual hypothesis test are supported with the result of this evaluation. Now, for question number 7, what distribution should the residuals of the regression follow? I'll repeat. Question number 7, what distribution should the residuals of the regression follow? You have 3 minutes. Start from now. You have 1 minute left. Thirty seconds. Okay, now the answer to that question is normal distribution. Now on to the next part. There is multicollinearity. Now, what is a multicollinearity? Well, multicollinearity is a statistical concept where several independent variables are in a model and they are correlated with each other. Now, two variables are considered to be perfectly collinear if their correlation coefficient is more plus or minus 1.0. Now, multicollinearity among independent variables will result in less reliable statistical interference, and it is better to use independent variables that are not correlated or repetitive when building multiple regression models that use two or more variables. Now, the existence of multicollinearity in a dataset can lead to less reliable results due to large standard errors. And then there's variance inflation factors, which is VIF. Now on to the next question. What is multicollinearity? I'll repeat the question. Question number 8. What is multicollinearity? You have 3 minutes starting from now. a second. The time is up. Now, the answer to what is multicollinearity is multicollinearity is a statistical concept where several independent variables in a model are correlated. On to the next topic, there is independent observations. Now, what exactly is a independent observation? An independent observations is any data point in a set of data which is statistically independent from the rest. Now, independence means that its value is not influenced by the value of any other observations in the set. Now you can see the graph from your left shows the residuals plotted on the vertical axis and the fitted values on the horizontal axis. Now note that the run of residuals above the mean of the residuals followed by a run below the mean. A scattered plot such as this would indicate that possible autocorrelation may occur. And on to question number 9. What is independent observation? I'll repeat the question. Question number 9. What exactly is independent observation? You have 3 minutes starting from now. You have 1 minute left. a second. And that is it. We run out of time. And what exactly is the answer? Well, an independent observation is any data point in a set of data which is statistically independent from the rest. Now, moving on, we are going to talk about qualitative independent variables. Now, qualitative variables aren't ordered by a numeral scale in statistics, so they are assigned nominal scales. Now, the word nominal means name, which is exactly what qualitative variables are. A nominal scale is a scale where no ordering is possible or implied, except for alphabetical ordering like New York, Washington, West Virginia, or Chelsea, Edinburgh, and London. Now, in other words, the nominal scale is where the data is assigned to a category. And then there's dummy variable, a variable in which there are only two possible outcomes. For analysis, one of the outcome is coded A1 and the other is A0.
Regression models with interaction. In regression analysis, interaction can be examined as a separate independent variable. An interaction prediction variable can be developed by multiplying the data values in one independent variable by the values in another independent variable, thereby creating a new independent variable. Here is a typical regression equation without an interaction. Y equals to B0 plus B1 times x1 plus B2 times x2, where y is the predicted value of a dependent variable, x1 and x2 are independent variables, and b0, b1, and b2 are regression coefficients. And here is the same regression equation with an interaction. Y equals to b0 plus b1 times x1 plus b2 times x2 plus b3 times x1, x2. Here b3 is a regression coefficient and x1, x2 is the interaction. The interaction between x1 and x2 is called a two-way interaction because it is the interaction between two independent variables. Why include an interaction term? The presence of an interaction indicates that the effect of one predictor variable on the response variable is different at different values of the other predictor variable. Adding an interaction term to a model that drastically changes the interpretation of all the coefficients. A model without interactions assumes that the effect of each predictor on the outcome is independent of other predictors in the model. So, into the question number 10. What are other situations that can occur when studying interaction? Please answer this question in 3 minutes, starting now. Time's up. So the answer is first, it is possible to have a three-way interaction among the independent variables. Second, it is possible to have an interaction where one of the independent variables is nominal scale. An interaction plot is a line graph that reveals the presence or absence of interactions among independent variables. To create an interaction plot, do the following. First, show the dependent variable on the vertical axis and an independent variable on the horizontal axis. Second, plot mean scores on the dependent variable separately for each level of a potential interacting variable. And lastly, connect the mean scores, producing separate lines for each level of the interacting variable. So from the graph in the plot beside, the lines are parallel. This suggests no interaction effect based on gender. The drug has the same effect on men as on women. For both men and women, 1 milligram of drug lowers anxiety level by 0.2 units. And for this graph, the lines are not parallel. The line for women is steeper. This suggests a possible interaction effect based on gender. The plot tells us that the drug reduces anxiety more effectively for women than for men. Question 11. How do you tell the lines from the interaction plot? One minute left. Time's up. So the answer If the lines are parallel, there is no interaction, while for not parallel, there is an interaction. In the table, notice that we have expressed gender as a dummy variable, where 1 represents females and 0 represents non-females, in this case males. Notice also that the variable in the third column, dg, is an interaction term with a value equal to the product of those times gender. Without interaction, from the picture, we see that both dose and gender are statistically significant at the 0.05 level, and with further analysis, we find that the coefficient of multiple determination is a respectable 0.80. With interaction, we see that the interaction between dose and gender is statistically significant at the 0.001 level. When we examine the main effects, we see that dose is statistically significant, but gender isn't. And finally, the coefficient of multiple determination is 0.99. How to interpret results? Assessing the statistical significance of the interaction term and comparing the coefficient of determination with and without the interaction term. If the interaction term is statistically significant, the interaction term is probably important. And if the coefficient of determination is also much bigger with interaction term, it is definitely important. If neither of these outcomes are observed, the interaction term can be removed from the regression equation. So from the table, the interaction term is statistically significant, p equals to 0.000, and r squared is much bigger with the interaction term than without it. It means 0.99 versus 0.80. Therefore, we conclude for this problem that the interaction term contributes in a meaningful way to the predictive ability of the regression equation. Stepwise regression. Stepwise regression is a method of fitting regression models in which the choice of predictive variables is carried out by an automatic procedure. In each step, a variable is considered for addition to or subtraction from the set of explanatory variables based on some pre-specified criterion. The stepwise method developed the same regression equation, selected the same independent variables, and found the same coefficient of determination as the global and individual tests described earlier in the chapter. The advantages to the stepwise method is that it is more direct than using a combination of the global and individual procedures. So there are three types of stepwise regression. The first one is forward selection method. Begin with no independent variables and add one independent variable to the regression equation at each iteration. Second, backward elimination method, which begins with the entire set of variables and eliminates one independent variable at each iteration. And lastly, bidirectional elimination is a combination of the first two methods. The advantages to the stepwise method are: first, only independent variables with significant regression coefficients are entered into the equation. Second, the steps involved in building the regression equation are clear. And lastly, it is efficient in finding the regression equation with only significant regression coefficients. Into question 12, define what stepwise regression is. 1 minute left. Time's up. And the answer is stepwise regression is the step-by-step iterative construction of a regression model that involves the selection of independent variables to be used in a final model. It involves adding or removing potential explanatory variables in succession and testing for statistical significance after each iteration. Review of multiple regression. Multiple regression analysis allows researchers to assess the strength of the relationship between an outcome, the dependent variable, and several predictor variables, as well as the importance of each of the predictors to the relationship, often with the effect of other predictors statistically eliminated. And that's all for our presentation, and please don't forget to leave a like for this video. Thank you.